Hello and welcome to Astronomy with Mr. Guerin. In part 1 of Objects in the Sky, we looked at what we can see in the sky, and in part 2 we looked at constellations and asterisms. Today we're going to consider how planets and stars appear to move through our sky. But first we'll look at the Sun's motion. Over a year, the Sun appears in different parts of the sky as the Earth moves through its orbit. The path the Sun traces out is a circle which defines a plane called the ecliptic. Or, seen another way, the Earth's orbit around the Sun defines the ecliptic, as seen in the animation on the left. On the right is a standard star map in right ascension and declination. To understand this map, see my celestial coordinates video. The yellow path is the path the Sun takes over a year. Because the Earth's rotation is tilted at 23.5 degrees to the ecliptic, this path moves 23.5 degrees above and below the central line, the celestial equator at 0 degrees declination. This star map, which also shows most of the asterisms you should know for the GCSE, shows the Sun moving from right to left, or to increasing right ascension, over the course of a year. Note how the Sun is at 0 declination at the equinoxes, 21st of March and 23rd of September, and reaches maximum and minimum declination at the solstices, 21st of June and 21st of December. As it travels, the Sun moves through the 12 traditional signs of the zodiac, the zodiacal constellations. There are actually 13 zodiacal constellations. Ophiuchus is one, but don't tell astrologers. When the Sun crosses the celestial equator at the spring equinox, it enters the constellation Aries, so we call this the first point of Aries. And when it crosses back again at the autumnal equinox, it enters Libra, so we call this location the first point of Libra. However, since these points were defined in 130 BC, precession has changed this, so that the Sun is now in Pisces and Virgo on these dates. Again, probably don't tell astrologers. Other objects in the solar system move roughly in the same plane, although not perfectly. The zodiacal band is a region, shown here in grey, 8 degrees either side of the ecliptic. All 8 major planets move within this band, from right to left, as we and they orbit the Sun, as you can see here with locations from the 21st of July 2017. Even the dwarf planet Pluto spends most of its time in the zodiacal band. Only some small objects like comets deviate much from this region. As mentioned, the planets move from right to left as they orbit. However, they all sometimes appear to slow down and then move backwards for a bit, from left to right. After a while, they return to their normal right-to-left motion. Here we can see Mars performing this odd dance, which is called retrograde motion. Of course, the planets don't really reverse their orbits. This is just an optical illusion, caused by the fact that the Earth is also orbiting the Sun, but at a different speed. When the Earth and the other planet are roughly in line in their orbit, the Earth overtakes outer planets, or lags behind inner planets, and our line of sight to the planet moves backward. Now, let's talk about how to find and identify planets in the sky. Because they move relative to the stars, star charts don't usually include them. The one I showed you before is useless except on one specific day years ago. These days, many people use a smartphone app. Sky Map for Android and Sky Safari for iPhone are both popular and free. I prefer Stellarium, which currently costs £3. You can point your phone at the sky, and the app will tell you what you're looking at. Or, if you want to find something, you can type its name and follow an on-screen arrow. This works for stars, planets, nebulae, galaxies, and often more. These apps use your phone's compass, and bear in mind that inbuilt compasses aren't always reliable, especially in built-up areas with lots of electromagnetic devices such as Wi-Fi. There are also many computer programs available. Stellarium is free on computer, including Windows, Mac and Linux, and you can print out custom star charts for your observations. There are many other such programs, and some let you plug your computer into a high-end telescope to control their steering and find objects to observe. And, if you found the maths in the celestial calculations video quite easy, you can use some programs and websites to generate text coordinates of specific objects at a certain location, date and time. You can see on screen the data I used to chart the locations of the planets that we saw earlier. There are also many excellent print and digital astronomy magazines. Two of the most popular in the UK are Sky at Night and Astronomy. These include many pages of star charts for the month and region they're sold in, with details on what interesting objects you can observe this month and how best to find them. You can also find a lot of videos online that go into the same kind of things, and I highly recommend Dr. Becky's Night Sky News Monthly, linked in the description. Dr. Becky is enthusiastic and great at explaining cutting-edge astronomical research in easy-to-understand ways. Finally, if you're just interested in observing the stars tonight, you can use a planisphere. This consists of a physical main body with an elliptical window and an inner rotating disk. The main body has a circle annotated with the time of day, and the disk is annotated with the date. When you align the current time with the current date, the window shows you the positions of the stars currently above the horizon. You can buy a professional quality planisphere, or download and print your own for free with just a printer, a pair of scissors, and a split pin. See the link in the description. In astronomy, we use a lot of technical terms to describe where astronomical objects such as planets are, and you should know what these mean. Here, Venus is at superior conjunction. This means it's in the same direction as the Sun, but on the opposite side of the Sun, so it's impossible to see Venus. All planets can be at superior conjunction. Here we see Mercury at inferior conjunction. It's in the same direction as the Sun, but on our side of the Sun. You can only see Mercury with specialised equipment at this time. Only inferior planets, Mercury and Venus, with orbits closer to the Sun than ours, can be at inferior conjunction. Here we see Mars at opposition. It's in the opposite direction compared with the Sun. This gives the best visibility for the planet, but only superior planets, with orbits more distant from the Sun than our own, can be at opposition. Here we can see all three. You may wish to print a copy of this for your notes. Of course, most of the time, planets aren't in line with the Sun. They have an elongation, which is the angular distance between the planet and the Sun. In this diagram, we see Venus and Mercury at their greatest elongation. These planets can be hard to see as they're usually very close to the Sun in the sky. Greatest elongation gives us our best view of the inferior planets. Note that at greatest elongation, the Sun-Planet-Earth angle is 90 degrees. When a superior planet is at elongation 90 degrees, the Earth would be at greatest elongation to observers from that planet. As we mentioned earlier, the planet's orbits aren't quite in the same plane as the Earth's orbit. They are inclined to the ecliptic, typically a few degrees off. And so, when Mercury and Venus are at inferior conjunction, they're usually not exactly in line with the Sun. But when they are, they transit across the Sun. We can see this with specialised equipment, as in the left image of Venus transiting across the Sun. Transits can also occur with other bodies, and on the right we can see Io transiting across Jupiter and casting its shadow on the clouds below. Transits occur when the nearby body appears smaller in the sky than the more distant body. But when the nearby body appears larger, it can occlude the more distant body, block it out entirely. We usually talk about planets occluding stars, but in this video we can see the Moon occluding a star in the lower left. Lastly today, we'll look at the apparent motion of stars over a day as the Earth rotates. For more on this motion, as well as the definitions and some more maths, see my celestial coordinates video, which should help you understand this section in more detail. You've heard of the cardinal points, north, east, south and west. In astronomy and navigation, these refer to the Earth's spin, which defines the geographic directions, rather than the Earth's magnetic field as shown on a compass, which is a few degrees off and varies over time. If you're using a compass, you have to adjust your measurements by a few degrees. You should also know the zenith, the point in the sky directly above you. There are a few definitions of meridian. The one we're using today is an imaginary circle in the sky. Trace a circle from your zenith above you, down to the horizon due south, then down below you and around to the horizon due north, and finally back up to your zenith. All points on this circle in the sky are on your meridian. As the Earth rotates, the stars change their apparent position in the sky, tracing out a circle in the sky once every sidereal day, which is 23 hours 56 minutes. When a star is highest in the sky, at its highest altitude, it is at culmination, also known as upper transit. At the opposite side of the star's circle, at its lowest altitude, the star is at lower transit. This occurs half a sidereal day, or 11 hours 58 minutes, before and after upper transit. Upper and lower transit both occur at points on your meridian. Upper transit, or culmination, occurs halfway between a star's rising and setting times. This is a good time to observe a star, since it's highest in the sky. The angular distance between a star and its nearest celestial pole, north or south, is known as its polar distance. We can use this distance to calculate the altitude of upper and lower transits. Upper transit altitude is your latitude plus the star's polar distance, and lower transit altitude is your latitude minus the star's polar distance. A star's declination is its angular distance from the celestial equator. Since the celestial poles are 90 degrees from the celestial equator, a star's polar distance is just 90 degrees minus its declination. Some stars never set from a certain latitude. If the polar distance is less than your latitude, the lower transit is above the horizon. The star never sets, and it is called circumpolar. We usually use the circumpolar equation. A star is circumpolar if 90 degrees minus the star's declination is less than the observer's latitude. Try the following questions. For each star, calculate its polar distance, upper and lower transit altitudes, and whether the star is circumpolar. The observer latitude is plus 52 degrees, or 52 degrees north, and the stars are Mizar, declination plus 55 degrees, Vega, declination plus 39 degrees, and Rigel, declination minus 8 degrees. Pause the video now to try them. For Mizar, polar distance is 90 degrees minus declination, or 90 degrees minus 55 degrees equals 35 degrees. Upper transit is latitude plus polar distance, 52 degrees plus 35 degrees equals 87 degrees. Lower transit is latitude minus polar distance, 52 degrees minus 35 degrees equals 17 degrees. And 90 degrees minus declination is 90 degrees minus 55 degrees equals 35 degrees. This is less than the observer's latitude of 52 degrees, so Mizar is circumpolar. For Vega, polar distance is 90 degrees minus 39 degrees equals 51 degrees. Upper transit is 52 degrees plus 51 degrees equals 103 degrees from south, which is the same as saying 77 degrees due north. Lower transit is 52 degrees minus 51 degrees equals 1 degree. Because 90 degrees minus 39 degrees equals 51 degrees, which is less than 52 degrees, Vega is circumpolar. Alternatively, just note that the lower transit is positive. In other words, the star's lowest point is above the horizon. And finally, Rigel's polar distance is 90 degrees minus negative 8 degrees, or 98 degrees from the north celestial pole. Upper transit is at 52 degrees plus 98 degrees equals 150 degrees, or 30 degrees due north. Lower transit is at 52 degrees minus 98 degrees equals minus 46 degrees, below the horizon. And 90 degrees minus negative 8 degrees equals 98 degrees. This is not less than 52 degrees, the observer's latitude. And, as we noted, the lower transit is negative, below the horizon. Rigel is not circumpolar. Here we can see these three stars as they might appear at night, showing their polar distances and the circles they trace out as the Earth turns. This picture shows a large amount of sky, from the horizon to the south at the bottom, up past your zenith, and most of the way back down towards the north. It would be difficult for you to take in this view all at once. Lastly, these three screens show a summary of the terms we've discussed today, as well as the equations we used and what retrograde motion means. Thank you for watching. Goodbye. and have an excellent day.